Okay, so the last thing we're going to be covering in this section on motion and dynamics is the idea of systems of multiple particles. So when we have one particle, we can pretty easily model it with a handful of equations. But when we have systems of particles that all interact with each other, it becomes a tad bit more complicated. So when we have our different forces that we think of in the real world, we have like a frictional force, a normal force keeping us above the, keeping us on the ground and not falling through it. But when we think of, or drag, for instance, but when we think of fundamental forces, because these are all forces that kind of arise from interactions between atoms and so forth, but they're not very fundamental. The really fundamental forces we have are the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity, of which gravity and the electromagnetic force are really the only two that we're interested in here. So when we have these forces, say gravity and electromagnetism, they have intrinsic values that cause these forces to interact with other particles. In the case of gravity, it's the mass of the particle, and in the case of electromagnetism, it's usually the charge of a particle. So when we have, when we want to study how a certain body will interact or how it will evolve throughout time and how it will move, we need to know everything about its surroundings in a way. So if we had, for instance, a planet orbiting in our solar system, we'd need to know how the gravity of all the other bodies in the solar system, all the other major bodies at least, are interacting with the planet we want to study. So in this way, if we have, say, we want to model the force of the ith body, so the ith planet or charge or whatever, we'd need some force function as a function of the set of all of the position vectors in the system. So this means if we want to talk about the force of the forces acting on Earth, we need to know a force function that is unique to Earth, and let it be a function of all of the other position vectors of the planet that are affecting it. So in this way, we can then write that the force, so the mass of the ith times the acceleration vector of the ith, is some function, f being the force function, of all the other position vectors in the system. So we can break this down even further and say that the mass of the ith body times the acceleration of the ith body in the x direction is, or we can rewrite this actually as x double dot of the ith body is going to be the force and the force function of all the set of x directions. So all of the x components of the position vectors that would lead to this equation here, we deal with now here. And so we can say the same is true for the y direction. So that means we have our force function of a set of all y components, and in the z direction as well. So now that we have three equations that will let us model one particle as a part of a system, we can think of how many equations we need for a general system. So if a system had n bodies, we now know that we'd have to use at least 3n equations to figure out how to model each body in that system. Okay, so just one thing I want to note, that the notation of this gets kind of messy, or was kind of messy. So if we dissect what this means quickly. It means that, so here we mean that the force in the x direction of the ith body, so the ith body we're dealing with in the system, is a function of the set of all x positions, or set of x positions of all bodies in the system is equal to the, the mass of the ith body times the acceleration of the ith body in the x direction. So that was kind of a notational thing that I don't think was clear towards the end of the first explanation, but it's very important. It's kind of a messy notation, and we won't really be using it, but it's a good idea to have in your head. Okay, so the next thing we're going to be talking about in our system of movable particles section is the idea of a space of states, or a state space. It's an idea we kind of take from linear algebra and maths, and we're going to need to define what a state is first before we move into exactly what a state space is. So if we say that a state is, it represents all the information that we need of a particle or about a particle to model it, every possible piece of information that we could need. We would then say that a state space, or space of states, is the abstract space that covers every single possible combination of all this information. So it's a little bit more of an abstract idea, but we use it a little bit more towards the end or towards the next sections. An example of this in a discrete sense is like flipping a coin or rolling a die. So if we have, say, a die rolling, we don't know what it's in. It can be, say, heads up with a 1, a 2, a 3, a 4, a 5, or a 6. So we can discretely say what the state space of that die is. It's if we were to say the position 1, the position 2, 3, 4, 5, or 6. Same with a coin being flipped. It's either in the position heads or position tails. So that's the entire space of states. For the real world, however, things aren't nearly as complicated, or things aren't nearly as simple, rather. When we have discrete motion or discrete states in a die or a coin, we have a continuous space of states when it comes to in the real world. You can't clearly define the difference in steps, even in position. There is no discrete jump you can make. There's always a number in between two measurements you make. So this is why it gets a little bit more complicated. So when we were talking about a system with n bodies and using n equations to figure out how to model that body, we weren't really too precise about it, because that would tell us the acceleration, for instance, but it wouldn't really tell us how or where a particle is at the beginning, or how fast the particle is moving at the beginning either. It just tells us how a system will move forward. So in this way, we need to figure out two more equations that'll tell us where a particle is. So that's where we need our original OR vector from. So if we have the OR vector, or rather, the OR vector of the ith body, and we need to also know the velocity vector of the ith body. And with combined with our knowledge of forces, and so we can then model how a system will progress. So when we are thinking about how to model this, we have our acceleration. So we have our acceleration vector, or really our force vector. And we can say that the force vector, therefore, of the ith body is the mass of the ith body times its acceleration, which is nothing more than the mass of the ith body times the velocity of the ith body, or the time derivative of the velocity of the ith body. And so now we have an equation that will tell us how to get the velocity back. So if we now have the force vector of the ith body is equal to the mass times the time derivative of the velocity vector of the ith body, we do what we always do. We can integrate from time 0 to t, from 0 to t, dt, and that's how we can find now. If we carry over the m as well, we can get the velocity by itself. And so we'll divide both sides by m, and so we'll get this is how we can get the function of, or v of t by itself. So we'll find here the original position, and then our constant will give us our t as well. And because we know our acceleration is nothing more than f over m, we can rewrite this as at. So now that we have our velocity, we can do the same thing that we normally do and find our position. And this is how we can use the minimal amount of equations to find the position and the velocity as well. As we were saying before, we have 3n equations that model a system of n bodies. Now this kind of misses out on a few things. That when we have our 3n equations, that tells us where or how a particle might move forward or so, but we really need 6 pieces of information, right? We need the exact place of the particle where it begins, which is our x-coordinate, our y-coordinate, our z-coordinate, our velocity in the x, y, and z direction, because that tells us where it is and how it's moving at the beginning, and then our dynamical or our law which dictates our force is separate from that. So when we think of our state space needing 3n equations, we're not really getting the entire picture. In reality, we need to get 6n equations. And you'd be kind of asking a question, well, where do these other 3n equations come from? And they usually come from the definition of the velocity. So we have now that our force of the ith body is mi times the acceleration of the ith body, which is nothing more than mi times the time derivative of vi, which isn't more than the double time, or the second time derivative of the position. And then we can also say that the velocity itself is equal to the time derivative of the position vector. And these are really the equations that we'll need. So, or this is rather mi times that. So now we have our velocity and an equation that gives us our force of the ith body. We really have all the information that we need. So we have our ability to get our initial conditions in velocity and position, and we have our force telling us how the system will progress as time moves forward. Okay, so when we were talking about forces at the beginning, we said that we usually use the equation F equals ma, although Newton originally wrote it as the force being equal to the time derivative of the momentum. So we're going to have a look now at more of what we can use momentum for, and a thing called the phase space. So when we think about momentum in the idea of collisions, so if we think, if you can imagine you're getting hit by a ping pong ball going at 40 kilometers an hour, it's going to hurt. But if you then imagine a train moving at the exact same speed, it's going to hurt a lot more. So this kind of gives us our idea that although force is important in acceleration, mass also has some idea with velocity. It has some connection somewhere. And so that's where we kind of get momentum from. And we can rewrite the state space or the in terms of velocity or in terms of momentum instead of using velocity like we were using before. And this will come in handy a lot later on when we talk about Hamiltonian mechanics and so. So let's take the minute to kind of rewrite what we were talking about before. So here's our first equation. We can write that mass times the acceleration is equal to the time derivative of momentum. So this gives us our kind of first idea. Then we can also write that the time derivative of momentum, therefore, is the force vector of all the other positions in the same way that we had before. And then finally that we can just write that the velocity itself is the momentum over the mass of a particle. And with these equations here, we can pretty much rewrite how we define the phase space. So with these, or with this, rather the state space, in terms of what we'll call the phase space, which is the space of position and momentum, instead of what we had before, where we had our state space in terms of position and velocity. Okay, so the last thing we're going to be talking about in this section of motion dynamics is the idea of actions, reactions, and just general conservation of momentum. Now, the conservation of momentum is one of the key and arguably one of the most beautiful things in physics. But we don't really have the tools to really attack and motivate it yet completely. But we can have a look at what happens and get a good idea and some amount of an expression that shows why momentum is completely conserved, or momentum is conserved in these systems. So if we were to draw out first let's say, a system of different bodies that are interacting with each other, either by charge or by gravity or something. And we'll draw this blue one here. This is, for now, the ith particle. This is the particle we're going to be studying for the minute. And we'll have a look at all of these interactions. So, as we said before, in these systems, we have that particles will interact with one another. So all of these particles here are exerting some sort of a force on our ith particle that we're looking at. And so if we were to take, let's say this small f vector, and we'll denote it ij, and we say that this is therefore the force being exerted on the ith particle, so here, on this particle we're studying at, by whatever jth particle. So the jth particle could be this one, it could be this one, any of them, it doesn't really matter. But when we sum all these up, so as you said, this is our kind of key idea here, is that this is the force exerted on the ith particle by the jth particle. And this is kind of the pretty important idea that we realize that this is on the ith particle and by the jth particle. This is the notation that we're going to be using for later on. So that means if we just take up if we were to figure out what all the forces, what the total force acting on the ith particle is, we can figure out that that's just, the particle, the force exerted on the ith particle by each individual other body in the system summed up. So if it's the pull or the force exerted by this one and 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 this one, all combined, that gives us our total amount of force being exerted on the ith particle. So we can therefore say that big F this time of I is equal to the sum over J of Fij. Now, one thing to kind of realize is that if we flip them, so let's say we have our jth particle here, and this interaction is what we're studying just for the moment. The force vector, so we'll say it acts in this direction. So the force vector acting in this direction, which tells us that J is pushing more onto I than I is onto J, for instance. So that force vector is, say, negative coming in here. But then if we were to switch it around and we were to study J on I instead, it will be positive. So when we have these force vectors, they're called, and we're originally studying the one particle and we're seeing how it's affected by the other one, we can then swap these around and we'll get the negative. So we'll get that F of Ij is equal to minus F of Ji. So this comes from the complete force that J is acting on I versus I acting on J. They're being just reversed by the kind of vector notation that we've been using, or how force is a vector, rather. And so we can therefore say that the momentum of I, or time derivative of the momentum of I, rather, is the sum over J of Fij. Now, if we were to say, for instance, sum over I as well. So if we were to add up all of these ones, Ij, where J is equal to 1, 2, 3, 4, or however many particles there are, and we were to then sum up the reverse of it, we would get that these would all cancel out, right? So if we had F1, 3 would be equal to minus F of 3, 1. And so when we sum these together, so if we were to say sum over I of P dot I, we'd sum all of these different pairs and we'd get this time a double sum, so the sum over I of the sum over J of Fij. We can interchange these and it would make no difference. But all of these pairs, action-reaction pairs they're called, would eventually cancel out. So that's why when we would sum up all of these and then sum up all of the i's as well, we'd find that all of these cancel out, go to 0. So again, that's because when we add the vector that describes this going to the force on I being exerted by j, and then add that to the vector of the force acting on j by I, the two vectors would cancel each other out. And so that means that we have that the sum over I of the time derivative of pi is equal to 0. And as we've said before, in the mathematical prerequisite section of this, when functions are well defined like that, we can usually swap them out. We can usually swap these operators around. And so that we'll get the time derivative of the sum over I of pi is equal to 0. Now this means that when we think about it, well, let's think about this. So this here, the sum over all the momenta of the different particles can be classified as the total momentum in the system. So it's all the momentum of all the particles all added together. And if we find the time derivative of that, so i.e. how much it'll change over time, it's 0, so it won't ever change. So that means when the total momentum in this entire system, well, we've just proven that it won't ever change, which is the conservation of momentum.